All right, so we're going to talk very briefly, hopefully, about the formal definition of a derivative using some limit ideas. And some of you may have dealt with limits before, some of you may not have, so that might be sort of a new topic. But what I keep trying to stress about derivatives is that derivatives are just slope. And what are they the slope of? They're the slope of a tangent line. So if our function is just a line, and I pick any 2 points on this line, the slope of this is always the same. It doesn't change. So no matter where I am on this line, right there, the slope is 2. Right here, slope is 2. Down here, slope is 2. So this slope is always 2. It never changes. It's constant. If I look at a parabola, like 1 degree up from a line, the slope at any point on this curve is changing. It's different. So what the derivative does is it gives us a function to find the slope. It'll give us an equation that we can find the actual slope at any point in time on a curve, which is a lot more complicated than it is on a line. So for example, up here, if I wanted to know the slope over here, it is a tangent line just touches it once. It's a very horrible tangent line, but that is a negative, very steep negative slope. If I look over here, that is a tangent line slope that is positive and quite steep. If I look down here at the vertex, that is a perfectly horizontal line that is tangent, and that slope is 0. So the slope at different points on this green parabola is changing. It's always changing. It is not constant. So what calculus does is it gives us an equation that we can use to find the slope at any point on a curve. So thinking about it in terms of being slope, and I'm going to draw another quick parabola here. The idea of slope is that we usually have 2 points to find slope. So if I had 2 points on this graph right here, that would be an estimation, an estimation of my tangent line, but it's actually a secant line because it touches it twice. And so as I change the distance between these two x values, as that distance decreases, so as this x value approaches the one on the right, I'm getting closer and closer to the tangent line. So this is meant to be sort of a display of that. So here's a cubic function, and this would be, and this is the point I'm interested in, like what is the slope at this point? What is the rate of change of this function exactly at this point, instantaneously? So not between these 2 points, not an average, what we were doing in class a couple days ago, where you found maybe a point right here and right here, right on the 2 sides of that point of interest. You were finding an average rate of change, and that average rate of change got closer and closer to the true instantaneous rate of change because those 2 distances were almost nothing. They're really close to each other, really close to this actual point. But you need 2 points to find slope. So if I move the green point, notice that that line now gets closer and closer to what the tangent line would be. And then in this case, it's going to end up, that would be the tangent line right there. Boom, I hit it. But notice there's only 1 point. So how do I find the slope using 2 points? So what I'm going to talk about in a minute is this x value, this green point. The distance between that green point and the red point is getting smaller and smaller as I approach the tangent line. So that distance between is the limiting piece. I'm limiting that as I approach 0. That distance approaches 0. So very quickly, I'm going to erase all of this. This is very messy work up here, so I don't want it there anymore. And this is why I asked you to speed up my videos, because I do silly things like that in the middle of them. All right, so if I want to find the slope, I'll use the old-fashioned m. That really is it's y2 minus y1 over x2 minus x1, which really is just the change in y over the change in x. That's all it is. So we're going to do the same thing, but in our graph, we're going to use function notation. So if I wanted to use function notation, I would say f of x2 minus f of x1 over x2 minus x1. So that's all we're going to do, and we're going to use this, but what we're going to talk about in this second point is if I look at a graph I'm just going to use a parabola again just because it's quicker for me to draw. What I want to talk about is if this is one value of x and this is another value of x, so we will call this one x1 and this one x2 just for fun. But what I really care about is that this one right here is approaching this value over here. So what I really can say is if I come down here and I change some of this notation, I could call this x, and I could call the distance between these 2 points, that distance is some distance h, which would make this second point x plus h. So now this is my second x value, and this is my first x value. So I don't need to use this x2 and x1 anymore. I can do it in terms of a single x. So that would be the value of f of x plus h minus the value of f of x. And again, that's giving me my output values. So if this is x plus h, then this right here would be f of x plus h. Some quick notation. And this one here would be f of x. And so when I'm talking about rise over run and slope, like this is my rise between, that's my rise, difference between those two y values, and this is my run down here. So like you probably used to do this, make little triangles. That's all we're doing. So that means if this is my second y output value up here, my first y output value, then down here I have x plus h. So I'm doing it in the same order. That's my second x value minus x. And so this would give me the slope of any point, any distance away from my original point h. So this is sort of the thing that's changing. And what I want to do is I want this distance between these 2 points to get smaller and smaller and smaller. So that's where I bring in the idea of a limit. And I say the limit as h approaches 0. So the limit as this distance right here goes away and becomes nothing, I will be finding the slope of the tangent line. So as it is, it's a secant line. If h is anything bigger than 0, that's just 2 points. But as h approaches 0 and gets closer and closer and closer to 0, infinitely close to 0, I'm finding the tangent line, the slope of the tangent line at that given point. So I'm going to just clean this up a little bit, and then you're going to have your formula for finding a derivative. The only thing I'm going to clean up is this down here. I have x plus h minus x, so these x's can cancel. So the actual definition, the limit definition of a derivative, is the limit as h approaches 0 of f of x plus h minus f of x all over, and see that's all that's left down there, all over h. And I'm going to put a big blue box around this because this is not the cleanest whiteboard experience you've encountered. That's what you want in your notes. And to think about this, as h approaches 0, if I were to plug 0 in here for h, this would just be f of x. And if I plug 0 down here, it'd be 0. And I'd have f of x minus f of x, which equals 0, over 0. And we all know that that's indeterminate. We cannot have 0 divided by 0. So that's why it is the limit as h approaches 0. And we're going to look at some algebraic techniques to use this limiting function to be able to find the derivative function. So that's what's going to come next as an example. This is the formula you want in your notes. We're going to use it. I will say that sometimes instead of h, people use delta x, meaning the change in x. So this could be the limit as the change in x approaches 0 of f of x plus delta x. And then this would be a delta x. So it's just swapping variables that mean the same thing. H is that distance on this graph, this little distance here that I'm going to minimize. And that's also the same as the change in x. That's the difference between my two x values. All right, I apologize for the sloppiness on this whiteboard. Next up, an example of how we can use this to find a derivative function.